Hello everyone. Thanks for joining this online session conducted by BIS on DSO capturing and instruments. So today we have Subhankar with us, who has been with BIS since the last 12 or 13 years. Me and Subhankar, we all started astrophotography at the same time, looking at Dr. Suresh Mohan taking wonderful astrophotos. And Shubhankar has given many talks with BAS in our earlier workshops as well. So this series of sessions that we are conducting during this lockdown period, we have already covered planetary imaging by Prabhu Kutty, and then telescopes and instruments by Anish. And today we have the DSO astrophotography setup. We will continue these sessions in the next weeks as well. So next we will have astro image processing, and then we will have visual observation by Akash Simha. And then we will also have Milky Way photography, and we will continue this series for quite some time. So let's start the session, and over to Shubhankar.
Thank you, Kirti. Thank you, Vishwa, and thanks for all the other past organizers. Am I audible, Kirti? Vishwa,
Yes,
somebody?
yes.
Yeah, okay. My name is Subhankar, and I have been associated with BAS since maybe more than a decade now. It was 2008, 2009 when BAS conducted a similar workshop on astrophotography, which is what I went and attended. Kirti no longer remembers it. Kirti was there, Doc was there, and several other people. Akash was there. So I had some background on photography already, and I've been in astronomy, interested in astronomy since my childhood. So it was like a logical progression for me to get interested in this beautiful hobby. So that's how I started my journey into astrophotography. So, and it's been a quite a journey so far. So with that, let me start. Today's topic is deep sky astrophotography. As you probably know, astrophotography has many sub-branches. Astrophotography could be done on a fixed tripod. Astrophotography could mean that you want to capture photos of moon or planets. Astrophotography could mean something like with a part of Earth and the sky together. It's a more of a landscape with the image, with the elements of astronomy in it. So what we are going to talk about a branch of astrophotography that is quite interesting. So what is deep sky astrophotography? Just give me a second. Sorry for that. So what is deep sky astrophotography? So here we are talking about photographing astronomical objects that lie beyond the solar system, such as the nebulas, galaxies, and the star clusters. So when it comes to photography, we always talk about zoom factor and how far it is, and etc. etc. So in terms of focal lengths, on a APS-C kind of sensor or a micro four thirds, we really use an objective which is like a 50 mm plus. From there onwards, below that it becomes a wide angle astrophotography, which can be done on a tripod, fixed tripod, etc. For most nebulas, we use about 150 to 500 mm kind of focal lengths, and one galaxy that is quite big that comes within that kind of focal length is M31 or Andromeda galaxy. For rest of the galaxies, we need far higher focal lengths, 800 mm plus. So if you translate that focal length with respect to these sensors, it comes to about about 30 degree to 0.5 degree uh, on the longer range. That's the kind of field of view we are talking about. So it's a wide range, and accordingly, the kind of equipments and kind of uh, approach we take to take this kind of photos also vary. Okay. In terms of exposures, we in deep sky astrophotography, exposures are usually long exposure. Uh, in few cases, we need to do few seconds of exposure, but mostly it is always above 30 seconds. Uh, Typically, it would be all 3 minutes to 5 minutes to 10 minutes. It all the way goes up to all the way up to 20 minutes in cases, and we take lots of exposures. Okay, okay. One of the thing that we all astronomers suffer in the beginning is aperture fever. So we want to go as deep possible. So we buy a small telescope, and then after some time we are not happy. We want to see deeper and further. The similar thing happens in the astrophotography also. So we get into this aperture fever. We start with a small, humble 1855 kit lens, and then we want to go further and further and further. Uh, but as you go further and further and further and buy more equipments, bigger telescopes, and more aperture, you start understanding things are really difficult as you scale up. Uh, and also, it adds to your cost and expenditure, because it's not just adding another telescope. You need to buy several associated accessories. Uh, and plus, to solve each of the difficult problems that you face, you end up buying more things. So that's that. So in astrophotography, there are three things, three primary stuff. So one is the equipment, the stuff that you use uh, to take the photographs. For example, your telescope or lens or camera, and a mount which will track the stars, etc., and all other related accessories. And then you capture the photos, and then there is something called a processing. As Kitty said, today's topic is about the equipment and capturing, and next weekend we will have a session on processing. But understand that these three you know building blocks sort of interact with each other. So when we capture with the intention of processing. So some part of the planning already happens, how we are going to process our image. With that, keeping in mind, we capture certain things in a certain way. And to capture certain things in a certain way, certain equipment needs to be configured or used in a certain way. So initially, when we start, when we learn into this hobby, we start very humble, tripod and probably a tracker and a camera. We learn, we capture something, then we take it to processing. We learn there, okay, what we have captured and what we wanted to do is really not sufficient. So then you come back and fine tune your capture process, or you fine tune your equipment to do better. It is continuous improvement and continuous learning, either direction and all directions. Okay. It's really weird for me to speak this, give a presentation like this where I can't see the audience and not able to interact. So I will stop often, and if you have questions, please type in the questions. Kirti and Vishwa will coordinate and ask me, whenever I stop for questions. I'll stop often. So don't just wait for the very end of the presentation, because it's a very long presentation. So if you have questions, type in right away, and we will try to answer them at the next break. Okay. So I'll show you some of my photographs. What I mean by deep sky astrophotography. So this is a photograph I'd taken of Milky Way, summer Milky Way primary region. This This
We
part
don't see your desktop.
actually, yeah, Kirti?
We don't see your desktop. I think you have to share your desktop.
I am sharing, no?
No,
Wait a second. How do I'm not able to pull this up.
Subhankar, you have to click share screen below.
Oh, okay. I'm not been sharing. Okay, let's begin from the beginning then. You should have pointed me out. Okay. We already talked about this. What is deep sky? Let me just go through again. So we are talking about capturing beyond the solar system, nebula, galaxy, and star cluster, about 50 mm to all the way to 800 plus mm is kind of the focal length, field of view about 30 degree to 0.5 degree on the horizontal side, and exposures. And I say difficulty increases with increasing focal length and decreasing field of view. Then I talked about equipment capturing and process being interdependent on each other. When we go out and set up our equipments and start capturing, aspect of capturing and how you use your equipment ultimately results how good you will be able to process it later. Okay. So this is some of the pictures I would like to show. This is a 50 mm field of view taken using Canon 50 mm. This is a Milky Way, summer Milky Way, part of the summer Milky Way, and the central location of the Milky Way, what is known as Sagittarius A stars, lies somewhere around here. So we see the Lagoon Nebula or M8 and the Trifid here, and the Swan and the Eagle here, with Cat's Paw down here, and several other jewels.
so what is the field of view of this?
Yeah, somebody is Kitty.
What is the field of view of this image?
50 mm, so that would be about 25 degrees, I guess.
So it's like the size of Orion constellation.
Yeah, it's a 50 mm field of view on a APS-C. So yeah, Orion constellation, yes. Orion would fit inside this view, just about.
Okay.
Okay. So this is taken using a 300 mm f2.8. This shows a part of the Orion constellation, the Bernard's Loop, and the M78 nebula within that. So just very near to very near to Orion's belt, going towards the top part, towards Betelgeuse. This is a picture of a star cluster, M41. And finally, I'll show you an image of, I don't know, Kirti, if you remember, we took this image at Koratgede one evening when the supernova 2014 J exploded. This is in M82. So this is a M81, M82, M81 and M82. So the Bodes galaxy and the Siga galaxy. Okay. So to do deep sky astrophotography, what do we need? First and foremost, in deep sky astrophotography is a mount. We need a platform which will track the star reliably for a long duration, for us to take a long exposure shot on top of it when we mount the camera and telescope on top of it, without trails. That's the goal. Optics, we can use lens and telescope and camera, DSLRs, CCD, CMOS, Astro camera. Throughout this presentation, I mentioned CCD, CMOS, even DSLRs are CMOS. So basically what I mean to say is these are specific dedicated Astro camera they look very different. I'll have some pictures later on. It does not have live views and autofocus mechanisms, etc., etc., like DSLRs. But these are dedicated camera designed for astronomical photography. There are traditionally these has been CCD, but nowadays we also have CMOS based camera gaining popularity every day. Then we need filters for light pollution, contrast enhancing. Then there are filters which are known as narrowband, LRGB. To house those filters, we need filter wheels, field correctors, spacers, then something called auto guider setup. To put everything together, we need some mountings. It's called dovetail bars, rings, and then all sorts of cables. Finally, we need to power everything. Dew is a big problem in our world. As the temperature during the winter time, as the temperature falls, dew also starts happening, and then we need a laptop most often to control all the equipments, and so that we can start the exposure and then go to sleep or do something else, and come back after 2 hours and review or etc. So everything needs to be done on its own. Finally, of course, you need a car, a lot of money to buy things. You need a location from where you want to shoot. You need a favorable weather, which is very difficult to get in the latitude where we live in. And you need lots of patience. Okay, any questions so far? Okay. So
there is a question as to what softwares you're using, but I think you will cover that later, right?
Yeah, we'll be covering that later, yeah. This is a fairly long presentation, so we hope to complete it by 2 hours, but let's see. So we start with the first thing. What we need is a mount. So we'll start with the mount. So long exposure deep sky astrophotography is usually done on something called equatorial mount. So what's an equatorial mount? It has the mount has a axis which is known as the right ascension axis that has to exactly align with the Earth's own axis on which it rotates. So consider the circle as a Earth, where this is the north, it's pointing towards the North Pole, and this to the South Pole. Can you see my pointer, please?
Yes, we can.
Yes.
Okay. And this line being the equator. And let's say you are located at a certain latitude on the northern hemisphere. So the mounts typically have this RA axis, which needs to point towards the pole, or the north celestial pole, as we know it. So basically, that axis has to align with the Earth's own rotational axis. When we have done that, as the Earth rotates, and this tracker will also be switched on to track the to rotate at the same speed as Earth. The stars will then be we will then be able to track the stars. Okay, so hence the terminology that we use is called it's an equatorial mount. So one axis is the RA axis, and the other axis is called the declination axis, or DEC in short. Okay. So this is that was just a figure. This is an example of how a mount looks like. So we have a huge, looks like this is a 10-inch f4 kind of telescope that is put on top of a mount with its RA axis, and this is a polar scope viewer. Through this, you can see the pole star on the northern hemisphere and counterweights, etc. So there are two axes on which this will rotate. One is around this axis. The telescope can go either east or west, and around this axis, the telescope can be rotated towards the north or south. Is that idea clear, right? So around this axis, around the RA axis, we would be, the scope would rotate from east to west, and around the deck axis, the scope would rotate towards north or south. Okay, so for mounts, there are various options. So throughout this presentation in astrophotography, there are many, whether you talk about mounts or talk about cameras or talk about telescopes, there are many options from the very DIY options, very cheap and etc., to options that cost $20,000 kind of stuff, very expensive stuff. So I'm going to limit my talk to equipment options that are affordable range by mortal human beings like myself and like yourself. We are not going to be talking about things that are really ultra expensive stuff. Um, I'm keeping that. So there are many things that people use and people do. We would not be touching upon them. So we would be touching upon the options and stuff that most commonly used by most common folks, so to say. So in case of mount options, everybody has heard of Bondo trackers. That is do it by yourself. You can and then you can put a small ball head kind of stuff and put a camera and a small not telescope, sorry, a small lens like 50 mm or so, and you can take shots of the sky. A little, step up from the Bondo trackers would be portable star trackers. These usually do not have a go-to. Go-to is a function in which you can ask the mount to go to a particular location in the sky. So the mounts would have a database of its own within its farmer or the keypad, and so we can select an object from that database and say go to that object, and it will then instruct the motors to rotate either in the deck and the array or the both to go to that object in the sky at that time. So portable star trackers typically don't have any go-to. I have not seen a portable star tracker being used more than 200 mm. Probably I have seen with 300 mm f4 being used, but certainly not 300 mm f2.8. So typically we can use up to 200 mm objective, etc. Some of them has an auto guiding port. We will learn about auto guiding later, but just for the information, since we are talking about these mounts here, so some of these star trackers have a auto guiding port. Some options that I have mentioned, iOptron, SkyGuider tracker, Skywatcher, AstroTrack. There are many options in these days, and every year I see at least 2 more new options coming up. This is a area where lots of innovations are happening. Other than that, then comes another step up is for heavier equipments. So these are proper German equatorial mount. These are heavy. The mount itself pretty heavy. I have Orion Atlas EQG. That the mount body itself is more than 15 kgs weighs. The tripod itself weighs about 10 kgs. So these are not portable as such. You can't just put them in a bag and take it in an airplane. It's not that simple. So these mounts will have a plethora of options like go-to, periodic error corrections, auto guide ports. It will have object database. It will have support for ASCOM. ASCOM is a platform in astronomy. It's an interface come platform which provides connectivity options with anything that is an astronomical equipment. We'll talk about ASCOM a bit later. Even in German equatorial mounts, like I said, there are entry levels, there are mid levels, there are pro levels, there are ultra pro levels, all sorts of options. So some of the manufacturers are Skywatcher, Orion, Celestron, Ioptron. They generally offer entry-level stuff plus the mid-level options. Then comes pro-level people like Astrophysics, Paramount, Lost Mandy, Takahashi of the world. There are even more ultra pro-level guys out there. So these are some of the portable star tracker that we have in the market currently. So it's pretty simple equipment. Uh, this is the entirely the equipment. The ball head does not come part of it. Of course, the ball head is yours, uh, but it will have a bolt to correct the altitude, and a couple of bolts to correct the azimuth. Altitude is the what you say, the height of the um, uh, axis, and the azimuth would be on the parallel on the ground. So these two things we need to move to align the polar alignment to align this axis for the polar alignment. This is where typically there will be a polar scope. So that means when you're doing a polar alignment, that time you cannot house the camera and the equipment. Once you do the polar alignment, you put it in. So most of these star trackers have that problem that you cannot. Uh, you have to put the load after you have done the polar alignment, and in doing so, you might actually cause a polar misalignment. So that's not too much of a problem if you're not trying to really push the equipment to its limit. Like you have put a 300 kind of lens, and there is a polar misalignment. It's not going to track properly. So as you can see, this is probably the Skywatcher one, and it has an auto guide port here and several options. Actually, you can do even a time lapse photography using this. Um, this is a peculiar mount. It's called Fornex. Forgot light track. Yeah, Fornex light track. This is actually works by a spring loading. So this has a trouble of it can track only up to a couple of hours, like AstroTrack, but it looks very simple and its tracking accuracy is very good. But only problem is it will track for a couple of hours, and then you have to restart it, rewind, and then restart it again. So this is how a portable star tracker would look like on a tripod. You need a sturdy tripod. If you don't kind of Manfrotto 55 kind of stuff. But even after that, you need to really put some sort of weight to really hang it down. This is how it looks like in a field usage. We would not be talking too much about this star tracker. So this is the only reference that you have. Mostly we'll be now going into the other mounts and deeper part of astrophotography. For doing astrophotography using this kind of mounts, there is not much. You use the polar scope to polar align. There are various kind of apps which help you to do the polar alignment. When you look through this particular polar scope, you see a reticle, illuminated reticle, some circles and some markings, and then you run an app, tell which kind of model it is that you want to polar alignment, and it will tell you where to put the bolster given your location and the time. So, and that's it, and then you start shooting. For the bigger mounts, this is the kind of options. The leftmost one is similar to what I have. It's Orion Atlas EQG. This one is probably Ioptron's M60. Kirti can confirm. And this one is Mighty, Paramount Mighty, one of the pretty expensive mount nowadays. So if you notice the difference with these guys and this one, look at the tripods. It's really thick and heavy. But even these tripods are sometimes are not enough. We need to change the tripod a lot of times. A lot of times what happens is you load put a lot of load on the telescope, and the counterweights come down too far down, and it starts to touch the tripod legs. So sometimes we use uh, something called a pyre mount, uh, a pyre base to house the mount for that purpose. I think I have a picture of that later. So this picture shows you a mount fully loaded. Uh, so this is the equatorial axis, or the RA axis, looking towards the North Celestial Pole. Uh, in this particular case, it has an electronic polar scope attached with the telescope and the guide scope. We'll talk about guide scope later. So, so um, around the RA axis, this is the RA axis. When it rotates east-west, and around this axis, when it rotates north-south. If you want to go and buy a mount, no matter whether it's a small star tracker that you're buying, or you're buying a proper German equatorial mount, these are a couple of things, a few things that you need to keep in mind. What's its load capacity? Load capacity usually mentioned in pounds or kg. Uh, so it will say the load capacity is 50 kg, and there will be a fine print, or it may not be mentioned, that whether that capacity includes the counterweight. Counterweights are these are the counterweights. You need to balance the mount later. So if you put 15 kg of equipment here, you need 15 kg of stuff there. Not exactly, but yeah, these are called counterweights. So when we say mounts loads capacity, whether, and it says 50 kg, whether that includes the counterweight or not is a question that we have to ask. If it's not specified, if it's specified, it's good. Typical wisdom in the astrophotography world says that whatever the load capacity that the manufacturer specifies, you take about 75% of it and mark that your max. First of all, you find out what is the load capacity without the counterweight. Let's say without the counterweight, the load capacity is 30 kg. And then you take 75% or 80% of that. I mean, that is your max. You don't just go and put it 30 kg. Can I make it 1 more kg extra, 33 kg, sir? No, sir. That's not possible. You will be pushing your mount too much, and probably be endangering the worm gears and the teeth and etc. So don't push your mount. Make a limit to up to 75 kg. So buying this kind of mount is basically it's a lifetime decision. When you buy a mount, it's not like you buy today and you want to upgrade 2 years later. That does not happen. First of all, the options here in India, available options are quite limited. And if you want to buy it from outside, it almost costs double by the time you get it shipped and pay the taxes for it, shipping cost plus the custom cost. It becomes almost double. Uh, so it's not like every day you'll go and buy a mount. So when you buy a mount, you think about what is your dream, what is that you want to do, uh, uh, what kind of photographs you want to do. And through these presentations, I would like to tell you, some of those aspects. Uh, at the end of the presentation, you should have a good idea of what is the realistically you can expect to do. So then you should look at the mount's tracking accuracy. Almost every mount in its specification would mention what is expected periodic error peak to peak. A periodic error is basically, the mounts are run by gears, and these gears are never going to be absolutely perfect. Uh, so no matter how it is done, there are different technologies involved, but how it is done, sometimes it will track faster, sometimes it will track slower. On an average, it will track at the same rate as the earth rotates. But So there is a wavy or a pattern which is called the periodic error. The peak to peak means the maximum and minimum error, the difference between the two. It's mentioned in the arc seconds typically. So what is the peak to peak periodic error? That defines its tracking accuracy. Is a polar alignment, whether there is a polar scope, usually all of them will have. Uh,
The Celestron mounts don't have polar scope usually, right?
Really?
I think so.
Celestron mounts don't have. Well, I have a picture of the Celestron. This is a Celestron, right? No. Oh, I did not know that.
Vishwa,
They
Vishwa, can you?
do have, but there is a slot that you can buy separately and then put it. But usually out of the box, it doesn't come with a polar scope.
Oh, okay. Okay. I did not know that. So some of the small trackers, what happens is the polar scope comes in the way. For example, this is the latest version of Ioptron, the one that I have. It's a much earlier version. And in this latest version, it is retracted. The polar scope sits like this. The earlier version, the polar scope used to be like right here, and it would extend all the way up here. I think Kirti also has the same model Kirti knows. So it comes in the way of tracking. So what we have to do is take out that polar scope. Once we have done the polar alignment, and after we start tracking. Otherwise, sometimes we cannot even frame it properly because the polar scope comes in the way. And that causes a number of issues because if the after framing you again want to do a final polar alignment check before you start the shots, and if your polar scope is going to get obstructed by your framing, then you're gone. So this is a better design that Ioptron guys have done. But for example, the other fellows, this is another Ioptron model, I guess. In this particular case, the polar scope is blocked by the ball head. So it means that you have to do polar alignment, and then you have to put it on top of it, and then believe that during the time you're doing compose and etc., you're not going to lose the polar alignment at all, and that is impossible. You will always lose. So what I mean by polar scope must not come in the way is that the quality of knobs, reticle markings, all typically the smaller ones, these knobs and all that are flimsy. So if you the Ioptron one that I have, I know that if I move the azimuth correction, it actually changes the altitude for some reason. So it's very difficult.
Yeah, the Vixen Polari also has the same issue. It doesn't come with a polar scope, but even if you buy a polar scope, it is in the same place as where you put the ball head. So you can either do the polar alignment or put the ball head, and it's crazy. Ioptron is much better in that sense.
Yeah. So typically, those kind of star trackers you should only use for very short focal lengths. Don't go above 50 mm. It's not meant for that at all. So
yeah, one more point which I would like to add is like when there is no visibility of Polaris, it is almost impossible to align.
Not almost impossible. You can do DRV and you can do standard things that we normally do in a drift alignment. But yeah, it is difficult. But drift alignment can still be done. If you have if you have the equipment, yes. Yeah. But if you don't have that kind of guide scope or camera and you want to do, there is a process called DARV using which it can be done. It's the same as drift alignment where you expose, okay, that's later. Let's not confuse people. So some of these scopes, some of these mounts have integrated bubble level, some of them don't. You need an integrated bubble level because leveling is the first thing we do in configuring the mount for polar alignment. It's important. Now, the power requirements, some mounts in astrophotography world, it is pretty much standard. The power required are 12 volts. I mean, there hardly any equipment that takes more than that, or it's not a 12 volt DC supply. But there are certain mounts, typically the higher grade ones, they are different. They need 24 volts or even higher. So be careful. I for a long time has been considering mighty, and then I realized that the mighty power requirements are different than 12 volt, and I dropped the idea. So also it is very costly. But that is one of the reasons that I wanted to have everything in the same power level, so that I can reuse battery. And you need to think about different battery for if you want. You need to supply 18 volts or 24 volts or 32 volts kind of stuff. Study tripod or pair. I already spoke about it. Important software and firmware support. If you have ASCOM driver for a mount, it's good because you want to control everything from computer ultimately. Pulse guiding if it has, again, good because you don't want to depend on ST4 guiding. And finally, you should always go through the reviews and user experience. So this is an example of a pair mounted mount. So instead of the tripod part looks like this, and there is a mount. So here, basically, we mitigate the risk of the counterweights hanging down, touching the legs at all. Okay, typically at our latitude, which is 13 degree. So if you look at here, the polar axis is almost looking 45 degree up. So that means it is 45 degree north or south latitude. We rather stay in a 13 degree latitude. So for us, the axis would rather be much somewhere like this. So which means this particular axis would be somewhere here. So if you have tripod legs extending, you can see that it can touch the tripod leg. So most of the manufacturers don't think of using, because these equipments are mostly used in Europe and US kind of places where polar axis is far higher. Okay.
So is there a minimum latitude below which these can't be used?
Yeah, some mounts do
specify.
specify. Yeah, there are mounts which specify that 10 degree north or 10 degree south is the minimum. For that, you have to use a wedge. They also say that you need to buy this wedge and put this wedge and stuff.
Mm-hmm.
Okay, I need to take a break, so just go to toilet and come back.
No, people are liking it. So everybody says they are understanding this.
Okay, great. So we move on to optics. Okay, so first we talk about the lens.
Sorry, just a second. I think somebody has marked something on the slide. Can it be erased? There is a yellow line.
Is it me? I have no idea.
I think it's somebody else. Somebody who typed or somebody who wrote OK or something like that. Okay, now it's fine. Let's go ahead.
Got it. Okay.
So if you are moving to mounts, I have a question. Sorry, if you are moving away to optics, I have a question on mounts. So
yes,
any experiences on hybrid mounts? So my understanding of mount is it can act or real.
Your voice is breaking.
See, this is what my thinking. So essentially, if I want to do some kind of visual observing from my place, obviously the number of stars I could be seeing is very less. So in that case, I think the best option is to go for a go-to mount. So
okay.
Go-to mount, I can't see the Polaris. So an alt-azimuth mount. Yeah, so an alt-azimuth mount, I can use probably a couple of stars, right? Because I'm not doing astrophotography. I can use a couple of stars to align, and using an alt-azimuth mount, I can, what do you call, align and start doing a visual observation.
Okay.
But I would also, maybe down the line, I would like to do visual photography, sorry, astrophotography. In that case, I don't want to invest again. So any observations or things on a hybrid
there is a Mount Jagan, which is AZEQ6 by Orion.
Okay.
Just I will search right away.
No, there is one from Orion. There is one from Ioptron. So the only question is that are people using it? How do they find it? And can we disengage the levers so that I can easily move it? Let's say I have a dark sky. I would like to do some star hopping, or I would like to easily hop.
I have no idea how easy to operate on it, but people are using it. Yes, that I know from the Cloudinate forum discussions. So how many people are using it? I do not know. So this is how it is. Can you see the screen? Can you see my screen?
Yeah, you may have to zoom. Okay. Yeah.
So this is how this mount looks like. It is.
Okay. Yeah.
The way it shows. Okay.
Can you click on the picture? Will it show it in the big picture?
Excuse me?
If you just click on the picture, will it show it in full screen?
Yeah. So this is in AZ mode, in which you would use it for a visual observation. So you can rotate in this direction and rotate in this direction. So it is same as your visual observation. So either you'll rotate on the what is this AZ, right? And what do you call this? Altitude.
Yeah.
So either this. So this is your visual observation mode, and the early one. So this will be the photography mode. So as I see, this particular component is extra.
Okay.
So in AZ mode, you have to discard this part. You can see, right? You have to discard this part out and put this body on top on the tripod. You're getting it, right? It is not as easy as unlocking some clutch and moving it, and that's it, done. No. And these things are not light. They will be weighing quite a lot.
Okay.
Okay. Does that answer your question? So you have to go through your review, Jagan, and to find out.
I mean, I think the problem for visual would be only that the eyepiece will be in a different position if you're using Newtonians. But if you use SCT, then you can still use EQ mount and orient it in any way you want and easily see it.
Okay. Yeah. Yeah, I'm good for now.
Also, for visual, it is quite difficult, especially with the Newtonian. The eyepiece can come in a very weird places.
Yes. Yeah, I know that. Yeah.
Okay. Shall we go on?
Yeah. Yeah, sure. Thanks.
Okay. So moving on to optics now. Optics first, lenses. So in case of when it comes to use in astrophotography, we prefer the primes over zooms. The primary reason is zooms will have a lot of glasses inside, which means internal reflections and a light loss, and I don't know what all other kind of basically that. And so primes are far better over zooms. And if you must use a zoom, then usually you choose an internal zoom over an external zoom. The most kit lenses are 1855 is a zoom lens and it's an external zoom. But 1855 is also a very good lens, and it's not as flimsy as the other um, zoom lens. I have a I think 20 to 105, which if you just leave the zoom, it slides back uh, by gravity. So the zoom is not fixable. It will just slide back. Um, so hence we do not prefer using zoom lenses usually for doing astrophotography. For serious work, primes are preferred. Of course, anywhere in astrophotography, it's faster the better. You choose f2.8 lens over f4 and over f5. LCDs are better with weather sealing. By the way, this is the time to clarify that I'm a Canon guy. Um, when astrophotography, in astrophotography world, Canon were much ahead than Nikon in terms of having cameras that are modifiable or having a camera which factory modified, etc., etc. Nikon came later, but as of now, uh, Canon, Nikon, Sony, any kind of DSLRs and their lenses can be used um, and have been being used by the people all through this series. I have no experience, absolutely no experience with Nikon or Sony at all. Only thing is I know is Canon. So I think it is called something else in case of Nikon. It's not called LCDs, but similar things are there in Nikon as well. So understand that my terminologies I'm using here are for Canons, but similar stuffs are also there for Nikon if any of you are Nikon.
Any Nikon guys in this chat who can tell us what it's called in Nikon terminology?
I think it's called a G lens.
SG?
G.
G series. Yep. Nano coated.
Yeah. So as long as you understand. so LCDs are better with weather sealing and etc. Weather sealing is important because we deal with dew all the time in astrophotography. Temperature will fall, things will become wet. You go to Kurk, no matter what time of the year, it will start dewing as soon as the sun goes behind the trees. So you need that weather sealing. Plus, you're keeping the lens all the night outside. I actually keep the lens even in the daytime. If I'm going there for 3 nights, for all the 3 nights, my equipment is outside in the sun, in the dust, in the wind, in everything. So the weather sealing and LCDs work very well. We will be covering this manual focus, etc. later, but at this point of time, it's good to highlight 2 things. And here we are always going to do manual focusing, except few cases where it is different. Remember to turn the focus to manual, and remember to turn off IS, image stabilization. It's very important. Actually, it is said in the photography world that if you're shooting on a tripod, you should turn off IS. IS is for handheld shooting only. If you're shooting on a tripod, you should always turn off IS. So extending that, here also you should turn off the IS. My 300 f2.8 is also used for, and I take it out for my normal wildlife photography or etc. So I have to remember to do all the settings when I'm taking it for Astro. Hood is an essential, so don't forget the hood, and must have a lens collar, especially if you're above 50 mm. 50 mm, it's fine. You can, but there is a challenge in the reason for lens collar is because of you're putting the things on an equatorial mount. directly. We'll show you some images how you put a lens on with a camera on an equatorial mount. For composition, you need to rotate. You may need to rotate the camera. The only way you can rotate the camera if you have a collar. Now, I'm talking about rotating the camera without changing the focus and etc. etc. You have to be very careful. You have done the hard work of focusing. Now you want to compose your shot, and you want to rotate the camera with the lens. So the only way to do it is to loosen the lens collar and rotate and then tighten it back. With the 50 mm, you cannot put a lens collar. So in that case, you actually have to mount it. Mounting is done on the camera itself. But then the recommended procedure is to use a ball head in that case alone. But other than that, for lenses higher than 50 mm, we don't use a ball head to put it on the stuff. We use something called a dovetail bar, which is attached to the lens collar, and then that assembly goes into the mount. So the lens collar is very important. Some lenses don't come. For example, 100 mm f2.8 don't come with a lens collar. You have to buy a third-party lens collar from the market. 200 mm comes with lens collar. No, 200 mm also does not come. Right? Can somebody confirm? I don't think it comes.
200 mm doesn't come with a lens collar.
Yeah. So 100 mm, 200 mm, but it has space for lens collar. 50 mm does not even have a space for lens collar. Yeah. You're saying something, Kitty?
No, I was just saying that you can buy a lens collar if you want.
Yeah, so the 100 mm, 200 mm don't come, but they have a space for the where you can put the lens collar, dedicated space where you can attach a third party off the market, off the shelf lens collar.
Yeah, somebody pointed out that 70-200 comes with a lens collar. That's right. But the 200 mm f2.8 prime lens, the black prime lens, sorry, black L lens, it doesn't come with a collar. But it's a very nice lens for astrophotography.
It's one of the popular. I mentioned that in the next slide. So usually with the lens, it has to be stopped down. For a daytime photography with a lot of light, you do not really see it, or even if you see it, it doesn't matter. Or you can easily correct by lens profile corrector in Photoshop or Lightroom. But in case of Astro, it becomes very complicated as well, because that vigneting, that field curvature, it's not just vigneting, it's also introduced coma. So your stars becomes funny shaped. It becomes elongated in 50 mm f1.8. If you're shooting at f1.8, and if you look at the corner stars, they look like small birds. It is weird. It does look like a small birds. So it is not correctable in any software. So 50 mm f1.8 has to be stopped down all the way to f4 or f4.5 to have the corner stars to look like stars. That is round, nice round one. We can tolerate a little bit of egg shapedness, but if it looks like a bar or a comma or a elongated or a semicircular, like a thin moon, thin new moon kind of stuff, those can't be corrected in software or in processing. So it is just not the vigneting for which you want to stop down, it will also to correct the coma. And usually because of this reason, the APS-C or smaller sensor works better rather than a full frame body. So even the full frame cameras have better noise responses. We still want to use the APS-C or smaller sensor like 4/3 with these lenses because of vigneting. Okay, so here are some of the options. Again, these are the Canon options. The similar options are there in Nikon and as well as Sony. I know for a fact. 50 mm f1.8, these are all primes. In case of Nikon, like Canon 200 mm f2.8 is very popular, like it just now mentioned, and it is one of the lenses which can be used wide open. And you have reasonable corner sharpness, uh, even wide open. A similar lens in the Nikon Kichi is a 180 mm f2.8. I don't remember the full name, but it is equally very popular. Uh, and I often use my 300 mm f2.8. There are other lenses by third-party manufacturer, which are very popular in the recent years. The Rokinon 85 mm f1.4 and the Samyang 135 f2.0 are very popular these days. And there are Sigma Art lenses, which are a bit costly, but they have a exceptional optical quality for use in Astro. Generally, we don't recommend or use the 1.4x and 2x teleconverters. I have though used, but if you're using, you should not be composing something which takes the entire field of view. You should a very narrow part in the center field of view. That's where the sharpness is still going to be there, but otherwise the sharpness really gets affected, especially with 2x teleconverters. So those teleconverters are usually not used. Okay, moving on to telescopes. As usual, we seem to think that aperture rules, but not always in astrophotography. It's the optical quality which is more important. So you can take better photographs using a lower aperture but better optical quality telescope than the opposite. Okay, but as usual, faster F number is better. In typically in case of astrophotography, the specific telescopes that are made for use in astrophotography are F4 or F5, F6, F6 kind of stuff. Whereas in visual, it can usually start from F5, or in some cases like CCDs, F9 or F11, where you don't mind, but F9 and F11 usually are not used for astrophotography. So what we mean by optical quality is the field curvature. Just like in lens, we have field curvature even here. It's a problem. Secondary color. There is a coma and the kind of coating used for used in the optics. For example, apochromatic lenses, apochromatic refractors versus achromatic refractors. So the refractors usually have two glass elements. They suffer from the secondary color problem, as was explained by Prabhu Kutty in his presentation. We have the comas, the blues and the reds separate, and so that problem goes away with the apochromatic by use of a third glass element. Hence, they're called triplet apo. That's where the triplet apo terminology comes from. So nowadays, there is even have a fourth element to tackle the field curvature. So it's called now quadruplet apo. So quadruplet apochromatic refractors have absolutely flat fields. Like I mentioned, weight of your scope is, and all with other accessories, camera, mounting, guide scope, this and that, everything has to be within your mount limit, and you should not push your mount limit to its absolute extreme. Usually what you get is what you pay for. And once again, remember that everything is tougher at a half of the length. I will again touch upon that sometime later with real data. Some of the options, like I mentioned, for refractors, for astrophotography use, always choose a apochromatic or triplet ED by minimum. If you can afford a quadruplet, it is flat field. Usually it is F6 or F7. For reflectors, there's something called imaging Newtonians. Usually they are all F4s. They have a very large secondary for better field illuminations. So if you compare a Newtonian telescope reflector and a the one that is made for astrophotography. This is the one of the biggest difference. The secondary is extremely large, not extremely large, noticeably large. Uh, so it's not that you cannot use reflector imaging Newtonians for visual purpose. There are couple of changes, couple of things you need to keep in mind. First of all, it will have probably less light to your eye. Secondly, the focus that this imaging Newtonians have are low profile. So what it means is you need to put some sort of extension rings, or use a coma corrector with a very long back focus in order to reach focus for your eye. Okay, but usually this comes with low profile and strong focuser. Bother, still track, moonlight, feather touch are usually common, um, but not always. My GSO imaging Newtonian, even though it says imaging Newtonian, it came with a very bad focuser, and it was neither low profile nor as strong, and I had to replace it with a moonlight later. Okay. There are other options that we use for RCs are usually f6 and f8. One only good part about the RC is that it's a flat field. SCTs are also used by some people, and a dock has a big one. It's very slow, so I don't think anybody uses it anymore in these days. So people either use lens or a refractor or a reflector. Again, most people means most people in our the common folks. Of course, there are folks which are outside these common folks. They use anything they can.
So Subhankar, there are two questions. So one is the lenses. We say, okay, some lenses are good, some lenses are bad. So what makes a lens good or bad?
Yeah, usually you will be looking at the corner sharpness and the vignetic. That is the one. So if you look at the zooms, they usually lack sharpness, corner sharpness, and the sharpness will fall off as you go away from the center. So some of the guys have done lens testing. So if you want to use a particular lens and you're interested to know how good is this lens for astro use, you go and check their website. Two persons I know. One is Jerry Rodriguez. He on his website he has published test results for many lenses. Another is Clark Vision. He also have published many lenses. In addition to lenses, Clark Vision also, is it called Clark Vision? Clark Vision is the website name. His name is Clark something. Clark. Is Doc here? He is Doc's friend, so doctor can tell the full name. So if you search for Clark Vision, you'll get that website. So apart from the lenses, he also has done the testing for different kind of DSLRs for astro use. And
I am here, Subhankar. I am here. I am just listening carefully, and if I have switched off the audio because I don't want to cut the bandwidth.
No problem. What's the name of Mr. Clark?
Roger Clark.
Roger Clark. Roger Clark.
Roger Clark. Yeah, there you go. So if you go to his website, you'll find test results for different kind of lenses. So both these guys. Shall I proceed?
There was another question, which was, can't the reflectors be made faster using reducers and correctors?
Yes, it can be. We will talk about that.
Okay.
Hey, I have a question here, Subhankar. I have one old Ashai lens, which is f4 200 mm tele, a prime lens. Do you think it is worth using it?
Yeah, why not? To try it out.
It's very old. Like I see, it's been with me from I don't know from how long, but I use sometimes for doing my wildlife photography.
Yeah, but does your DSLR come to focus with it?
Yeah, so it comes. It has a M42 ring type mount. So I have a T adapter for that. So I put it on and it works. works.
Yeah. So then, if you're able to use that old lens with the latest cameras, then you can certainly use it for Astro. Since prime, it should not be any problem. What you need to watch out for, take it wide open, shot wide open, and then go and evaluate the stars in the corner as you go um, away from the center. So open 1:1 view or zoom in and see the stars. So if you see, the star profile are getting worse as you're going away from the center. So no, you probably need to stop down. It does not mean that you cannot use. Now, how much you need to stop down is a factor of the lens, is a that we cannot say. So stop down by one stop may be okay. So going from f4 to f5.6 probably will be okay. If you have to go further down f8, it becomes too slow.
Okay.
Okay.
I'll try that. Yeah.
Yeah. So, but then there is nothing wrong. Even at f8, we can shoot certain things.
And there is another question. Any suggestion for upgrading the standard focuser which comes with the Newtonian reflector?
Oh, I already said these are the three best options: budget still track, moonlight, or feather touch, as per whatever you can afford. Budget still track is what is the cheaper one of the three. The moonlight, feather touch typically are pretty costly, but they are beautiful. All the three.
And do they come for different sizes of the OTAs, or are they all same with
Yeah,
some?
there are options. It will come with the. You need to be very careful about, whether you want a thin profile or you don't want a thin profile, because that will that is determined by where exactly your secondary is and where exactly your focus point is going to be for Astro. So that you have to carefully evaluate and find out. But all the three will come whether the options are available or not. But they provide different options for different kind of. So they're available for 2 inch, they're available for 3 inch, etc. etc. Yeah.
Okay.
I don't think they will
Any other
say that
questions?
it's made for DSO F4. It is made for Orion something or something. They may not speak, in that terms. The better is to contact the owner or contact the to directly them and ask them. This is the focuser I have, and you need to send some sort of dimensions. That's what I did when I upgraded my GSO 10-inch f4 from the stock focuser to moonlight. So I measured everything and sent him the measurements. Then he came back with the options that I should buy.
Okay, thanks.
Okay. Okay, moving on. So these are some of the telescope options: 80 mm f6, triplet ED by Explo Scientific, and there is a 65. So I just mentioned Explo Scientific 80 mm x6 triplet ED is made by many guys. It's not just, this is the one that I have. This is my first telescope, so it's just customary to put that name here. But 80 mm f6 triplet ED is quite a common configuration. So almost many people have it, or if not exactly, they have something similar like 85 mm or 75 mm or 70 mm, something nearby. Similarly, the next option has also become very common: 65 mm f6.5 quadruplet ED. And there are many guys again like Astrodirect, Telescope Express. So many people have that. If you want to step up your game in the reflector, then there is of course Takahashi FSQ, which Doc has, and believe me, it's a pain. But according to Doc will kill me. It's the best refractor in the world. I'm not going to debate that. Right, Doc? So moving on to reflectors.
I think Takahashi is the best.
Okay, Doc, we believe you. Okay, so moving on to reflectors, 8-inch, 10-inch, 12-inch, f4 imaging Newtonians by everybody nowadays. It's all over the place. It's so popular these days. 8-inch f4 is one of the most popular and the most economical reflector options if you're getting into this hobby, and you want to shoot a wide range of subjects using that. It's so if there is if I have to suggest two options out of uh, three optics you must have in your arsenal. One is a 200 mm f2.8 lens, which is very popular. Second option is 80 mm f6 triplet ED or the quadruplet one, but that you can forget. You may not want to buy. If you want to buy another one, it should be 8-inch f4 imaging Newtonian, and save your money to go as as loaded one as possible. So choose the carbon fiber. If you can choose the one with a already installed moonlight or feather touch or a bother still track. uh, don't do a post buying modifications. So when you're buying, buy with that. So if you go to Telescope Express, they give all sorts of options for 8-inch f4 Newton. They have options with carbon fiber. They have options with carbon fiber and moonlight, uh, or feather touch or still track, whichever focuser you want. So 8-inch f4 is the one to buy. Very recently, even Kirti bought one. I've got one. Doctor has got one. So many of us have 8-inch f4. Okay, so other accessories in case of that we use, fill flatteners. These are typically used for triplet approach refractors. Um, this again comes with or without a reducer. Couple of options I mentioned. There are plenty of options. You just search for fill flatteners. It's like you'll get 10 pages of Google results. The one that I have is a unique one. It's a 2-inch self-centering fill flattener. So basically, you turn the knob to tighten it. It does not have a thumb screw. So it's good because the things that have thumb screw has a tendency to tilt it. So I chose that because of that reason. Next option is a Skywatcher 0.85x reducer corrector. So essentially, light becomes flat after it, but it also reduces the focal length by that factor, 0.85. Coma correctors. Similarly, for coma correctors for Newtonian, again, here also it comes with or without a reducer. Some options are MPCC, the best uh, or the most popular coma corrector in the Newtonian world is Badr MPCC, and it's beautiful. It works. It's nice. It produces nice stars. Uh, I have two coma correctors. One is Badr MPCC I bought later, but I had a GSO coma corrector, uh, which is dual use. You can use it for both photo and as well as visual with an extension ring. But it's not nearly as good as MPCC. MPCC is compact uh, and it's nice. Again, ASA is one that doctor uses and he swears by it. So it is a reducer corrector. It reduces the focal length by 0.73x. So his imaging Newtonian 8-inch f4 becomes 8-inch f2.8.
Also my 12-inch.
Also on 12-inch, yeah. Why you don't have a 10-inch?
Since you have, I can always take it from you.
It's a win corrector, right? The ASA is 0.73x.
Okay. So, yeah. All these things have something called back focus. I will be talking about it a little later in detail. But remember, when you're buying any of these flatteners, correctors, etc., or even for telescope, you need to look at the specification and understand the back focus. Okay, more on that later. Any questions? No questions. So we move on to cameras. How are you doing on time? There is no way we can finish it by 9 o'clock.
Yeah, we have 25 minutes. So
Okay,
let's
go as far as possible. Then we'll take it on on other week.
Yeah.
Cameras. Okay. So when it comes to DSLR, there are few options. Standard unmodified stock DSLRs. Canon, Nikon, Sony. Everybody is in the game these days. And you can use any camera that you have, as long as it's a DSLR, and you can do those kind of shots. Can be used for taking astrophotography, astrophotographs. But when it comes to nebula, uh, you can use unmodified DSLRs to take shots of star clusters and galaxies, no problem. But when it comes to nebula, there is certain issue. Issue is this, that the visual, these cameras in the stock configurations, they put a IR cut filter uh, before their sensor. So that IR cut filter is designed such a way that ultimate image or its color response is similar to what human eye can see in a daytime. Um, so it cuts down a particular wavelength, which is 656 nanometer, and the deep infrared or the infrared part of that wavelength. wavelength. So most of our nebulas shines in HA or in that particular wavelength. So when we say modified DSLR, are the DSLRs that are modified to not have that kind of IR cutoff. Now, nowadays, Canon actually started this long time back. They used to have a model called Canon 20DA. Actually, this graph is for a 20DA. It's no longer available in the market. So this graph, not even 10D. 10D is also not available. So it basically compares the filter curve for response for the 10D and the 20D. You can see the HA is typically cut off at 25-30% level, whereas in 20D, so much of HA is passed through. So the factory modified DSLRs means that Canon themselves have come out with Astro specific models of 60D, and nowadays there is a new one called USRA. I don't have much idea about it, but 60DA is I know. And Nikon also have something. I'm not sure about Sony having a Astro specific model. If anyone knows, he can tell me. But I'm not aware of Sony having a. I did hear about A7A, but I'm not sure if it's a factory model or a somebody's modified model. So next comes third-party modified DSLRs. There are many people who have taken up, who has figured out how to take out that particular filter by themselves. It's a very complicated procedure, but the procedures are available in the internet. And if somebody is interested, you can do. Our very own Kirti Kiran has done it. So if you have questions on how to modify your DSLR by yourself, Kirti is the person to go and bug. Right, Kirti? So, but this modification service is provided by many folks in many different ways. Some even have completely re-engineers. Central DS in China is one of them. So they take out the entire body and rehouse it in a different enclosure altogether. So it does not look like the original Canon at all. It looks very different. They put the cooler, cooling, and etc. fan, and take out all sorts of stuff that's not required. I think autofocus is also not autofocus, but there are many functions which we just don't use in astrophotography are taken off. So So those are the third-party modified options. Here is an example of a modified versus unmodified stock of M27, the Dumble Nebula. Uh, this is unmodified. Here you can see it captures the blue light pretty well because the blue comes well within the focal length here. Somewhere here, 500 odd is blue. Uh, so the blue part of the nebulosity is captured pretty well, but the red part, which is somewhere here in between, is not come at all. So this is the response of the modified version where you see the red has come. This is the HA. This comes due to that HA wavelength. Okay. Another example, many people would probably recognize or appreciate this example than the other one. This is a terrestrial astrophoto of Milky Way with a part of Earth in front. So if you can see, I do see a bit of the brightness is not similar between the two photos, but if you can see the response between the modified and non-modified, as far as the registration of Milky Way goes, it's way better. Okay, so moving on from DSLR and its options, next comes the CCD. I'm not going to talk about CCD at all. CCDs are no longer preferred in the common astrophotographers who wants to use a cooled camera. These days, one little company in China called ZWO came out with a beautiful option of using a CMOS chip from Sony. Was it Sony or Panasonic? Yeah, one of them, and put a cooler around it and came out with an option for all us astrophotographers, cheap, beautiful in terms of sensitivity and very low dark current. These are the commonly wanted features of camera. The primary reason that we look at the dedicated astro camera is cooling. In the DSLR, what happens is, or not just DSLR, every camera sensor is there is a thermal noise. In a daytime photography, also there is noise with a high ISO and etc. But it's a factor of the thermal. Since we are going to expose for minutes, it's not a photograph that's taken at 1/250 kind of exposure. It's taken for 5 minutes or so. For that long, the sensor collects heat, and that heat or thermal generates noise. So, so one way to deal with that noise is to cool down the sensor artificially. Put a tech cooling just behind the sensor so that the sensor is cooled. So this is what the dedicated astro cameras do. So they are usually cooled, and minus 35 to minus 40 from ambient. It's pretty much standard. More expensive astro cameras cool up to 60, up to 80 also for a high end. More buck for the money. You have to spend a lot for that. So they come in either mono or a color. Color means there's a Bayer filter. In Astro world, it's called one-shot color. White is called one-shot, is because you can produce color picture using mono as well, but you need to take 3 different shots. RGB, actually 4, LRGB, luminance, red, green, and blue. 4 shots to produce a color image using a mono camera. Whereas a color astro camera, you can produce a color image using one single shot. That's why it's called one-shot color. But otherwise, the difference is basically between mono and color is the sensor. Out of the sensor, there is a Bayer filter. Okay, so typically this astro camera also have, they are nothing like DSLRs. They don't have autofocus. They don't have so much of electronics, nothing. It's very simple stuff. And through firmware control or software control, you can actually control the gain directly. Gain is equivalent to, somewhat equivalent to the ISO in the DSLR world. So these days, the CMOS cameras that we use lower gain and hence better dynamic range for galaxies and wideband imaging. And we use a higher gain and a somewhat lower dynamic range for narrowband nebula imaging, which higher gain actually results a very low read noise, which also allows us to take a shorter exposure, like 2 minutes or 1 minute, even 3 minutes shots, which in case of CCD, usually it requires 10 minutes or 20 minutes with an narrowband. Okay. So here is a a visual for the monochrome versus a color sensor. Doesn't matter the CCD or CMOS or DSLR. This is how it looks like. So this is what is known as a Bayer filter. It's in a RGGB pattern, always RGGB pattern, and different kind of way color camera has patterns differ, and you need to know the correct Bayer pattern used on your OSC if you're using OSC. What is the correct Bayer pattern, and you need to configure that the time of processing. You need to say my Bayer filter is RGGB or GRBG or something like that. You have to say in which order your Bayer pattern comes, so that the information can be whatever shot you have taken can be correctly processed. Kirti will cover that next week. Okay, any questions?
I have one question. You mentioned that we don't use CCD cameras anymore. Is there any reason why CMOS is preferred over CCD today, apart from cost?
No, it's not just the cost. It's the engineering actually. Cost is of course, but it's the engineering. Like I said, the new generation CMOS chips that we are using today in this particular this kind of cameras, it's pioneered by ZW, and now it's spread like wildfire across all other manufacturers, and they have caused a disruption. So these guys use the Sony or it's a Panasonic-based CMOS, and they could cool it down, put that engineering in place. So basically, took that particular CMOS chip, put a Peltier cooling behind it, a tech cooling behind it, and produce the low darkening noise at a higher gain, which enables the astrophotographer around the world to do narrowband imaging with a shorter exposure. So that is the primary reason why people are moving towards that direction. So narrowband imaging with a traditional CCD requires typically 10 minutes to 15 minutes, 20 minutes of exposure. So now you have cut that down to 3 minutes to 5 minutes. Or in some nebulas which are pretty strong or pretty bright, you can, for example, Carina, above 60 minutes, above 60 seconds is actually going to saturate. So that kind of sensitivity it has. So you no longer need to expose for 10, 15, 20 minutes. So you can do things with a shorter exposure and lots of exposure. Okay, so that has caused the disruption, and that disruption is spreading. So everywhere, everybody is nowadays buying the ZW or the QHY equivalent of these cameras. Yeah.
Thanks.
So if you had none of us would like to move away from DSLR, because we know the DSLR response. If we could just cool down the DSLR, we all love the DSLR. And if you try to answer why, so 1600 at 1600 ISO, we get the response of every nebula pretty well. Only problem has been noise. Only problem with the DSLR use is noise. So there are many different ways. 5, 6 years ago, people would design a box around it, and put what is that, dry ice, and to cool it. And there are so many different options came up. The only thing that we wanted is if there was a way to cool it. Then there came the engineering guys, Central DS, or who's the company in Holland?
JTW.
Huh?
JTW.
JTW Astronomy. So
JTW.
yeah. So they came up with the re-engineered versions of the modified DSLRs with cooling and etc. etc. Now, if you really see their game, they were trying to understand, trying to build what was so useful in DSLR with cooling. We are fantastic. We're done with it. This is exactly what the ZWO guys have done. Not with the Nikon or Canon. They have done it with the Sony and Panasonic chips.
Just one more question, sorry. Now take one of these new ZWOs or one of these QHY like you mentioned. Can it really compare with like a S-Big or a FLI, which uses a Kodak CCD? Would they actually compare well to some of the older but really good CCDs which we know?
What do you think, Doc? In my opinion, Doc is here, who has used, CAF 8300 best CCD, so he can answer.
Yeah, let me tell you, basically, when it comes to CCD, then there is something called class 1, class 2, and class 3. The SBIG, the higher end CCDs are all class 1 chips. That means the 99.99% each pixel is guaranteed to give you inputs, and they will cost you about $15,000. Whereas the CCDs used by Chinese companies, they're not class 1, but lower. But the point is, for a amateur astronomer like you and me, it will hardly make a difference, because unless you're into research, definitely the cost of SBIG would be 4 times the cost of QHY equivalent. But reliability factor on a QHY cannot be equated to what comes out of SBIG. For example, my QHY 10 has failed me more than 3 times. Now it's gone back to China for repair. So they'll change the whole thing and give me a new one. So that's no problem. But that's because I have contacts, people to carry for me. But if you get it and if you don't have connections, then it's going to be difficult after 3 years of life.
Yeah, but the question more was about image quality, Doc.
No problem. No problem. See, for image quality, there is virtually no difference, in the sense at the level of amateur level. 100% I can give you a guarantee. But they're a little bit of a pain, in the sense in the middle of the night the cable will come off loose. You'll have to be watching most of the time.
Okay. So
if everything works fine, then they're on par.
Yeah, the question was between the ZWO or QHY CMOS based new cameras versus SBIG or ETIC or FLI older generation CCD cameras. Image quality.
Well. Okay. Now, most of these newer version cameras are made for smaller refractors like what we have, and shorter focal length. See, finally, you'll have to calculate how many arc seconds per pixel of the sky you're imaging. And the FLI, there are cameras that have pixels as large as, if I'm not mistaken, 18 microns. Okay, and ours is about 3 to 4 microns. So there is a formula where you have to calculate the focal length and the area of your pixel that will tell you what portion of the sky each pixel.
Doctor, I'm covering it in a few slides down the line. So, yeah.
Sorry?
I'm covering that aspect, imaging scales.
Okay.
A few slides down the line. So, yeah.
Right.
Thanks for the answer.
You're welcome.
Okay, there is one more question on the chat. What about resolution when comparing CCD and CMOS? Doesn't CMOS sensors have more resolution in terms of megapixels than CCD?
Oh, we don't look at the megapixels. What we look at is the arc-second per pixel, something called image scale, which we would cover sometime later. So just wait for that.
So whether it's a 6 megapixel or a 16 megapixel, doesn't matter.
It doesn't matter. What you really look at the field of view and imaging scale, and you try to put the best optics along with it. So there are certain considerations that we have to make with respect to what is your ultimately imaging scale in terms of arc-second per pixel and your seeing condition with which you're going to image. So these two factors define what should be your preferred optics, and for that preferred optics, what is the preferred kind of camera you should use. Yeah.
Okay. All right.
So if you have a 30 megapixels packed into a very small APS-C kind of sensor, it means you have a very small arc-second per pixel. I'll tell you what happens when you use such a very small arc-second per pixel in astrophotography a little later. Yeah.
Okay. All right. There are two more questions, but probably we can take them at the end of the presentation.
Yeah, sure. So we move on to filters now. Okay. So the first filter, the one that we use very often is a light pollution filter. Light pollution, as we know, is the primary biggest threat to astrophotography. And primarily, whether it's a visual or photography, we look for dark sky, and we hunt for dark sky, and we lament that dark skies are reducing by the day. But this is life. So the light pollution filter is a filter that many of us use for subduing the light pollution to some extent. If you see the filter response, typically emit or eliminate the mercury and the sodium lines. So traditionally, those are the emission lines from the typical lamps. This light pollution filter, I'm not very sure that can actually handle the light pollution caused by the LED lights. Somewhere I've read it is not. It does not. So somebody can confirm if somebody knows anything about it. What I read that LED, the recent light pollution caused by the LED lamps are not possible to eliminate. So this shows an example with the light pollution filter and without a light pollution filter. This is M31 Andromeda Galaxy. So this side is without. This is how the exposure remaining same, and this is how it will look like. And this is the side where the with the light pollution filter. This is how it will look like. So you can see the kind of difference it has. So typically you get two stops of advantage. It darkens your field by a couple of stops at least. So you can extend. So if you did not have a light pollution filter, you can probably shoot. You can extend your exposure by 2 stops. That's what it means. So next we come to narrowband filters. There are varieties of narrowband. What is narrowband? sunrise. No, I don't have a graph. Okay, so most of the nebulas in the sky shines in a certain a particular wavelength, and there are three of them are very well known and popular. One is hydrogen alpha, it's about 656 nanometer, and then there is a oxygen 3, which is also known as doubly ionized oxygen, it's at around 500 nanometer, and sulfur 2 again in the red region, a little ahead of hydrogen alpha itself, it's 672 nanometer. So since this nebulas shine in one of these lights, or a combination of them, and if your goal is to capture those nebulosity only, then you can start imaging with these filters put on, as these filters only allow a certain passband around that particular wavelength. So there are grades of these filters. You get it in 6 nanometer passband, or 9 nanometer passband, 12 nanometer passband. Expensive ones even down below 3 nanometer passband. So you can see how thin. So it cuts off all other wavelengths. Only passes the that particular wavelength with the passband. More expensive ones, narrower, and etc. etc. So one primary advantage of using these filters is that you can now image from a light polluted area. You can do narrowband imaging from a light polluted area, put these filters on, etc. etc. Of course, you have to solve the other problems. How do you do polar line from a light polluted area, and etc. etc. But let's say you've gone past all that, and then you can image from a light polluted area. You can do imaging with moon up. Now, just like light pollution, astrophotography has a problem when the moon comes up. Uh, Moon comes up, everything just goes washes out. Not The narrowband filters don't get affected as much. It's wrong to say it does not get affected at all. Oxygen 3, O3 is really sensitive to moonlight. So when the moon is up, we don't really shoot O3, no matter where the moon is or the size of the moon is. But the hydrogen alpha and sulfur 2 can be done if the moon is 60 degrees away and stuff like that. With a thinner passband, you can do, you can shoot narrowband with the moon closer as well. Okay. A lot of creativity can be done during processing with the narrowband captured data, because these are all, first of all, captured on a mono camera. So you capture hydrogen alpha data on a mono camera. Then you can capture similarly oxygen 3 and sulfur 2. Then during the processing, you can assign that data in the different channels. And you can say that I want all the data that is collected as S2 to go into red channel, and all the data that connected as HA to go into green channel, and the O3 would be blue. So this is a palette. The palette is named after in the order in which you are assigning. The SHO palette, also known as Hubble palette. Just a second. The Hubble palette, first used by the NASA for processing Hubble telescope taken images of similar nebula. This is the Pillars of Creation, one of the famous Hubble photograph. This is the region in M16, the Eagle Nebula. A feature in that is called, the entire thing is called Pillars of Creation. And so this processing was done in a SHO palette. Similar, it is taken by amateur astrophotographer, a mortal entity, not a Hubble guys or NASA, by someone earthly. So this is Pac-Man Nebula, or is this Pac-Man, or I think this is a nebula which is beside the flaming star. Forgot what's the name of it, but this is again in a SHO palette. So similarly, you can experiment and use your creativity in different kind of palettes. You can also actually do mixing. You take half of S2, mix it with half of O2, and do pixel match like that. Take some of HA, put it into the red channel, take some of it, put it in the all sorts of mix and match. You can do your own creativity and come out with a color scheme that you like. Um, these are called false color or mapped uh, astrophotography. So in reality, this is not how the nebula actually would look if you had the eye to see it. This is not how the color of the nebula would look uh, actually. So these are false color or mapped images. Okay. So some of how do we now I have series of pictures of showing filters in different kind of configurations or different kind of cameras. So this is a DSLR with a light pollution filter. CLS CCD is a light pollution filter. So this is how if you want to use a DSLR with a lens, where do you put the filter? This is a big question. And you want to use it under light polluted sky. So the clip-in filter comes to our aid. So basically, this is how the filter comes, and this is how you put it actually. The filter will take it very carefully, push it inside, and snap it into paste into its space. With while you are at it, you should be taking care that no dust gets into your mirror and no dust motes, or you should not be touching the glass surface. For doing LRGB or doing a narrowband imaging with Astro dedicated camera, we use a filter wheel. So this is a filter wheel by ZWO guys themselves. This is a mini version. So it has 5 spaces inside. So basically there's a wheel with 5 holes. 5 holes goes by, so you can screw in the filters into those holes, or hold the filter in using this knobs, little thumb screws with stoppers in them. And this particular filter wheel has ASCOM support. So basically it means through software I can tell move to filter position 1 or filter position 2 and etc. And it's pretty accurate. The filter directly comes below the hole, almost every time perfectly below the hole. There is a little notch beside every filter. That notch is used for knowing the exact position where the filter wheel, the motor should stop rotating. This is another option. I also have one. Before I invested in a filter wheel, I was so desperate to use a filter. I bought something like this. Useless expenditure actually, but then that's how life is. Life is for an astrophotographer. So this is a filter drawer, which basically comes between your telescope and the camera, and you can slide in the filter and screw in the filter in the drawer, and then slide it in and screw it shut. So yeah. So in place of filter wheel, you can choose to use these. Okay. Now we move on to very complex stuff. Shall we stop? It's 9 o'clock. Iti, others, what do you say?
Yeah. So let's stop at this point. So since we completed one particular topic.
How many have we covered so far? Oh, man.
So how much?
40%. 40%.
Okay. All right. So I think we have some more questions in the chat. So maybe we can just take them. Okay. I had some internet problems in between, so I lost the question. So Vishwa, are you there? Can you read some of the questions that we left out?
Yeah, Kirti. I mean, there were not many questions. I mean, there was people actually asked with the mic itself. There is one question. One person. So he is actually preparing an f4.8 14-inch reflector. And is there any special consideration that he has to choose for using it for photography?
Okay. So what's the question?
Yeah. So are there
What should he keep in mind to do astrophotography with the 14-inch f4.5? So I think some of the points are you need to make sure that you have enough back focus so that you can do the photography with that. And then with these big telescopes, a lot of things come into play, like how do you track this? So maybe you probably use an Equatorial EQ platform. And also the other thing is the tube flexure, like how do you collimate, and how strong is the tube to make sure that the collimation remains. So maybe Subhankar, you can add some more points.
Yeah, those are the ones. So you need to look at the weight of the entire assembly, and then what is the material that you're using. So if you're going to use PVC, typically the homemade, a lot of us have used a PVC to make the body. So if that will cause flexure, definitely. With that kind of, so 14 inch is pretty heavy. If you're going to have a truss body, no, it is not appropriate for astrophotography at all. So it all depends on what kind of 14 inch is pretty big. Doctor has a 12 inch, and it's like, it's taller than him. So it's also 4.8. So it will be really tall. So and really big. So how are you going to put that on the mount is a big concern to me, actually. You need a pretty strong and pretty advanced mount, in my opinion. And you need to invest in a similar kind of setup. So you need the rings to hold it. You need the D-type. I was actually going to talk about all that later. The D-type mounting plates, etc., etc. And like Kirti mentioned, even before that, the primary concern is to ensure that your focuser is thin profile for it to come to focus with camera. Typically, f4.8 or f5 means your focus point is pretty far away, so you would be the focuser is thick for that reason. So it may not be.
I think that was a Dobsonian mount. I believe, yeah. The question says it's a 14-inch Dobbs, so I guess it is not possible for using deep sky astrophotography.
No,
yeah,
not a Dobson.
Yeah.
If it's a Strat tube, no, definitely no.
There's another question. So, any suggestions for buying a telescope for Skywatcher Star Adventurer? So that's a tracking mount, basically.
There is a beautiful. Why do you want a scope?
Correct.
So Star Adventurer, typically, like I said, the maximum you can usually go to 200 mm. If you want to push it, you can put a 300 mm f4. So you can do very well with a lens, which are probably more affordable, and you can buy off the market here easily than buying a scope. If you must buy a scope, I think one of those 65 mm quadruplet is pretty good option.
So
and there is also another option called RateCat 51.
Correct.
So just search for RateCat 51. It should. How do I? Creates a problem for me. Uh-oh. Just search for RateCat 51. Yeah. So there is a very cute looking scope. So it's 250 mm f5. Out of stock now. At $748. No picture is not even. Can you get see?
Yeah.
How do I make it full screen? Yeah.
There's one more question. So how do you perform noise reduction on LRGB subs?
Okay, that's Kitty's domain. Kitty will explain.
No, no. I have never done any monochrome or any CCD or CMOS photography, so I have absolutely no idea.
Now you first stack it and then align it and then combine it, and then LRGB means you have to do the LRGB combination and then you attack the noise. If you want to attack the noise before you want to do it, you want to do LRGB combination, there are ways to do it. So if it speaks about next week, I'm hoping that it will hit my mind, and then I will. Let's take this question later next week, and then we'll see. Okay.
In the linear stage, you can do the TGVD noise or.
Yeah. Now like I said, when you speak about it, it will come to my head. TGV noise reduction. Yes, there was one process which you can do in the linear time. Yes. So those are the ones you can use when it is still uncombined state and state. Yeah.
Yeah, I guess that's all. I don't see any other questions.
So what's the plan for continuing this? When do we continue? We will discuss and let people know.
Yeah, we'll discuss.
Yeah, we can have one session per week, so probably next weekend.
Yeah, I have no problem. We can do next weekend.
Sure.
All right. Thanks, Subhankar. Thanks. It was a wonderful session, and let's continue this session next time. And till then, thanks a lot, everyone, for participating and asking so many questions. Have a nice day. Bye.
Thanks, Subhankar. It was a really excellent talk, and from the fundamentals you went, and I think you covered almost everything.
Not yet, doctor. It's going to continue next weekend.
I mean, whatever you did today was exhaustive. Nice.
Okay, thank you.
You're welcome.
Okay, bye.
Thank you so much. It was super good.
Cool. Thanks, Johan.
Yep.
Okay. Thank you, guys. Good night.
All right.